My name is Judy Carminati. Welcome back to the C2Space Chronicles, where we share the messy, unpredictable, definitely experimental side of studying human physiology in extreme environments. We've already talked about designing this study to look at cognitive impairment, whatever that means, caused by nitrogen narcosis underwater. So the next step in designing the study was trying to understand what are we trying to measure and how much of that thing do we care about. And for this particular video, we were still focusing on the DSST, which is the test that we've been using in our pilot program and as we move forward trying to design this study. Now, there are three terms I'm going to talk about today. They are a power test, effect size, and variance. I'm going to give you an explanation. I'm going to repeat these concepts in a variety of different ways because I find that's most helpful when you're trying to understand something. But here's the thing, I am not a statistician. And so I'm also going to link in the description a video by StatQuest and a couple other videos I've come across that are truly incredible. And if you want to learn more about statistics, I strongly encourage you to check out StatQuest. They definitely got me through my statistics class. Before we jump into the definitions, we are going to define terms that are used to understand those definitions. The thing we need to really have in our heads is the difference between a type 1 and a type 2 error. Okay? So I really get frustrated when I go online and I try to look up these terms because I find these textbook answers that don't actually explain what's going on. And the reality is that type 1 and type 2 errors are actually not complicated concepts. They're just explained really poorly. So I'm going to read to you what the textbook definition is, and then I'm going to explain them to you in just regular words. A type 1 error is rejecting the null hypothesis in favor of false alternative hypothesis. And a type 2 error is failing to reject a false null hypothesis in favor of a true alternative hypothesis. Does that help? I don't think that helps. It drives me crazy. It's just basic science communication. I'm going to give it to you in way simpler terms. A type 1 is a false positive. A type 2 is a false negative. That should already start making more sense to you. A type 1 error is when you say that there is, in fact, an effect, but there was none. And a type 2 error is when you say there was no effect, but in fact, there was one. Does that make sense? Now I'm going to say it again in the nitrogen narcosis situation. So a type 1 error would be saying, oh, there is significant cognitive impairment underwater, when in fact there is none. A false negative would be saying there is no cognitive impairment underwater, when in fact there is one. That is the definition of a type 1 and a type 2 error. Now, a type 1 error is usually measured, the probability of committing a type 1 error, sorry, I have to say that again. The probability of committing a type 1 error is usually referred to as alpha. When you guys see something that's p is less than 0.05, 0.05 is alpha. What you're saying is that your p-value is smaller than alpha, and so there is less than that chance that you are committing a type 1 error. The other corollary to that is beta for type 2 errors. And now we can talk about a power test. A power test is helping you figure out what is your beta value. Power test is designed to determine the ability of your study to correctly identify a true effect if it actually exists. And importantly, it assesses the study's sensitivity to detective differences of relationships in the data. A high power indicates a better chance of identifying a real effect if it exists. So a little bit different than when we were talking about p-value, because you want your p-value to be really, really, really small, right? But for your power, you want a high power. So let's talk about the terms we were talking about before. So a null hypothesis is a default assumption that there is no effect or no difference. The alternate hypothesis, which is often referred to as H1, is the hypothesis that there is a real effect or difference between whatever you're looking at, right? So in our case, it would be depth and some cognitive impairment, right? That there is a relationship between those two, that depth does impact cognitive impairment. And then the statistical power is the probability that the test will correctly reject The null hypothesis will correctly reject there is no effect when there is in fact an effect, when the alternative hypothesis is true. Importantly, the power test will tell you how big a sample you need to be confident in that conclusion. And that's why it matters to us as we are designing this study. The effect size is a quantitative measure that expresses the magnitude, the size of a phenomenon or the strength of a relationship. So it provides a standardized way to compare the impact of the intervention, depth, right? Nitrogen under pressure, and the variable that we are looking at, which is cognitive impairment. And effect size is often used to complement the p-value and give a more comprehensive understanding of practical significance of the results. And now I'm going to say it a different way. So statistical significance will tell you that there's an effect, right? An effect exists in a study. But the practical significance is actually shown in the effect size, right? Is the effect large enough to be meaningful in the real world? So I'm going to give you an example. And this is something we're still struggling with. So this is just truly an illustration. Don't take these numbers to mean anything. But let's say that we find that there is a statistically significant decrease in your performance underwater, and that you will always miss, let's say on average, you will miss 3 more boxes, right? 3 more digits, symbol substitutions underwater than you do at the surface. Now, we can show that with statistical significance. That happens pretty regularly. But the effect size will tell us, do we care? Does it matter? Is it important? Because it might not. If, for example, we go out into the world and we find that you actually miss 3 more if you've had a couple cups of coffee, or you miss 3 more if you've been a little sleep deprived, or if you're stressed, or if you're a little colder, then do you care? Do you really consider that to be cognitively impaired in a way that matters? No, you wouldn't. We wouldn't. We would report the results and tell you we don't think cognitive impairment is a thing. And all of this is obviously theoretical. But the thing is, like, do those 3 points matter? Should 5 points matter? Should 1 point matter? Should 15 not matter? That's what we're trying to get at when we're looking at effect size. And that's why it's important to report both effect size and p-value, because there might be statistically significant difference, right? Difference in the variables, but it may mean nothing in real life application. And that's how you make science actually matter and actually answer questions that people are asking. And then finally, we are going to be looking at the concept of variance. So variance refers to the degree of spread or dispersion in a set of data points, usually around the mean. So usually it looks at how much an individual data point will deviate from an average of the data set. So a high variance means that there's a big spread, and a small variance means there's a little spread. And this is a key, again, to understanding the meaningfulness of the information that we are collecting. Because if your baseline on the surface with no narcosis before a dive shows that you will have a variance of maybe 10 points on the DSST, then if you go down and you score within that 10-point variance, what does it matter, right? Those are the questions we're trying to ask, and that's why variance matters. How much, in our case, we're going to be looking at how much does the baseline vary for each individual. If you actually have a very narrow spread, then we will have a very low variance, and therefore, as you are moving off of that range, we will probably be more interested and find that there is more significance, and I mean that in the late term, more meaningfulness to the data that we are seeing. No. So why do we care about all this? We care because there is a difference, an important difference, between positively showing that something has no effect and failing to demonstrate that it had an effect. If you're from the outside, you will look at data and think there's no effect. But does that mean that you have proven that there's no effect? or that you have failed to demonstrate that it did, that you missed it. And so in our case, the difference is between positively demonstrating that nitrogen narcosis has no effect on cognition and failing to show that there is an impairment on that domain. And the ability to detect a treatment effect with a given level of confidence will depend on the size of the effect, the variability within the population, and the size of the sample. The size of the sample matters because if your sample size is too small, you may fail to reject the null hypothesis, right? Because the statistical procedure lacks the power, we're back to that word, to detect the effect. But that's not because there's no effect. It's because your sample size is too small. So understanding the power of a test allows you to calculate the sample size. And that's really been kind of my obsession for the last 2 weeks, and I still don't have an answer. I'm going to talk again about false positive versus false negative. I think it's a helpful review. So we know that if the p-value is under 0.05, which you now know is a stand-in for the alpha value, right? Probability of committing a type 1 error. If the p-value is under 0.05, we can reject the null hypothesis. We can reject that there is no effect. Okay. So if I get a p-value of under 0.05, I can say that there is a statistically significant correlation between depth and your DSST results. But what about the false negative conclusion? And that's kind of what, well, now you're obsessing with me, but I've been obsessing about this for a couple weeks. What about the false negative conclusion? This is saying that there is no effect when there is, in fact, an effect. And in other words, we would be reporting that there is no impairment in cognition when, in fact, there is one. So the chance of detecting a true positive, that is reporting a statistically significant difference when the treatment really produced an effect, is 1 minus beta. This is the power of a test. So if a test has a power of 0.56, there is a 56% chance of reporting a statistically significant effect when there is one. There is a 56% chance of being right. The power of a given statistical test depends on the risk of error you will tolerate when rejecting the hypothesis of no treatment effect. That's your beta. The size of the difference you wish to detect relative to the amount of variability in the population. And that is a mixture of both the effect size and the variance, and then your sample size. So what does the research say? And I went off and I read over 25 studies using the DSST. And it was not great, to be honest, because there was a lot of reporting of statistical significance, but very little discussion of power tests and really very little comparison to baseline variance. And that gave me pause, and it really meant that we are going to have to buckle down and really figure out how to do this correctly. Thank you for watching. My name is Juji Carminati. These are the C2Space Chronicles, and I'll see you next time.